Gilly, I know we're working with grapes right now, but like, do you ever think about what the energy between two grapes would be? I know that sounds a little messed up, but like, everything
I passed
experiences
chemistry last year.
stuff that's falling to Earth, has like potential energy of like gravitation. But like, what about like stuff that's falling towards one another? It wouldn't be the same formula, because you use like baby G and stuff. Actually, I think I know the formula for that. I want one sec. Get out of here.
Alright, so we're going to talk about the formula that you use to find the potential energy of gravitation between two objects. We're not just going to talk about it though, we're going to show where it comes from. So there's two important things that you need to know to be able to understand where this formula comes from. The first one is that F sub g is equal to the universal gravitational constant times m1 m2 over r, all negative. And then the second thing is that this force fundamentally is equal to -1 times the change in energy over the change in distance. So that negative sign is there because an attractive force like gravity fundamentally has to have negative potential energy. This is basically because when these two objects get pulled towards each other by gravity, they gain energy in the form of kinetic energy, but due to the law of conservation of energy, gravitational potential energy must decrease by the same amount, meaning that all gravitational potential energy has to be negative, which is kind of weird, but just think about it for a second, it should make sense. So while I was talking, I did a bunch of calculus that gave us the formula for this potential energy, and that would be PE grav equals -g m1 m2 over r. Sweet. But wait, I can already hear you saying, isn't potential energy equal to just mg delta h? What the frick? Well, worry not, young child, because I'm about to tell you what's up. So that formula is actually the change of potential energy is equal to mg delta h. So it's delta u sub g is equal to mg delta h. And we can actually find this formula from our universal gravitational potential energy formula, which is pretty cool. That's what I'm going to do right now. So we know that the change of potential energy is equal to the final potential energy minus the initial potential energy. So u sub f minus u sub g, or sub I. So if we plug in our formula for both of those u's, simplify a little bit, multiply by r over r here and there, we get this weird looking formula with a bunch of things that don't look like the formula, but it basically is. So there's gm over r squared, which is baby g, there's some other stuff, and there's something that's basically 1, and all of that simplifies down to mg delta h times 1, which we don't care about. So yeah, that's how you derive the formula we've been using for potential energy from the universal one. Um, Keep in mind though that the formula we've been using, mg delta h, only applies to things on Earth. The great thing about -g m1 m2 over r is that it's a universal equation, which means it applies everywhere, anywhere in the universe, which is pretty cool or whatever. So the next logical thing to do with this stuff would be to solve an example problem with it. Now we could do any old boring example problem where M1 is some stuff and M2 is some other stuff and R is like a distance and then you just kind of plug in and solve for the potential energy. But that's boring. That's like 5th grade math. Like we're seniors, we can do better than that. So instead of that, we're going to do something slightly less plug and chug, but still pretty plug and chug. And we're going to talk about something very tangentially related to this, which is escape velocities, which is way cooler. So if you don't know what an escape velocity is, basically it's the velocity you need to be able to escape the gravitational pull of a planet, like Earth, for example. So that's what we're going to do. We're going to find out what speed do you need to be going to be able to get out of Earth's atmosphere and gravitational pull. Well, where do we even start with that? We have this potential energy formula, but how's that even related to this at all? Well, I'll tell you how. Through the law of conservation of energy. In this case, the initial energy is equal to the final energy in a closed system, which this is. So the initial potential energy plus kinetic energy is equal to the final potential and kinetic energy, which would just be 0. And through some algebra, you get V equals 2gm over r, or the square root of that. Using that, we can plug in and solve for our little velocity using the mass of the Earth, gravitational constant, and the radius of the Earth. And we get the escape velocity for Earth is 1.12 times 10 to the 4th meters per second, which is pretty pretty cool if you ask me.
Is grape pie a real thing?
Blackberry pie.
Yo, it's